Hello, today we are going to observe streamlines and streak lines inside a water tank. This will be accomplished by placing a 3D printed airfoil inside a tank and adding color dye water to observe the effects of the flow passing around the foil. First, we'll start by defining what exactly a streamline is and some basic equations in order to further understand the scope of this instructional video.
First, we'll start by defining what exactly a streamline is. A streamline is a path traveled out by a massless particle as it moves with flow. However, it is easier to visualize if we move along with the body as opposed to moving with the flow. At every point along the particle's path, velocity is always tangent to this path. Since there is no normal component of the velocity along the path, mass cannot cross a streamline. For this airfoil, we are only going to be concerned with 2D flow. Like I said before, streamlines are always tangent to the instantaneous velocity. The streamline can then be broken down into two components. With a traditional x and y axes, it can be seen that the differential change in the x component is equal to u. The differential change in the y component is equal to v. This allows us to obtain the equation for a 2D streamline, which is dy over dx is equal to v over u. This is an ordinary differential equation with v and u being a function of x and y. X naught and y naught are usually initial conditions of the system that are used in the differential equation to find the constants of integration.
Streamlines and streak lines are identical for steady flow. This happens because when a particle reaches a point on a streamline, let's call it a knot, further on that streamline, the equations governing the flow will send it in a certain direction. Applications for streamlines include aiding engineers to guide design modifications, helping to reduce drag force, which is actual process called streamlining. The resulting design is referred to as being streamlined. Streamlines are also frame dependent. That is, the streamlines observed in one inertial reference frame are different from those observed in another inertial reference frame. For example, the streamlines in air around an aircraft wing are defined differently for a passenger on the aircraft than an observer who would be on the ground. Therefore, if possible, it would be helpful to find a reference frame with steady flow, so experimental methods of creating streak lines in order to identify the streamlines. Here we have our airfoil placed inside the water tank. We built a simple mechanism that was capable of lowering and raising the airfoil inside the water tank in order to observe the effects when the height and angle were changed of the airfoil itself. We then used food color drops in order to see the effects of streak lines as they fell to the bottom of the tank. The tank had a drainage system that was open in order to pull the food color dye down to the bottom. However, because the drainage was causing an unsteady flow at the bottom of the tank, the effects were easily seen when observing the streak lines near the drain. There was obvious turbulence in the streak lines even though they were falling straight down.
To be able to tell if the velocity is increasing or decreasing by only looking at streamlines is possible by looking at the distance the streamlines are apart. If they are getting further apart, the velocity is decreasing. If they are converging, the velocity is increasing. In other words, the velocity is inversely proportional to the distance between the streamlines.
As we can see in the video, the airfoil acts as an obstruction to the flow of the particles. The particles slow down and diverge around the airfoil. Beyond the tip of the airfoil, velocity increases to the initial value as there is no obstruction and the streamlines converge.
A proper understanding of streamlines can be useful in fluid mechanics. Besides velocity, pressure can be measured through the curvature of the streamlines. The center of curvature points in the direction of decreasing radial pressure. A relationship between pressure and velocity can then be derived from Bernoulli's principle for the location along a streamline.
Streamlines have many uses, but one of the most important comes when the Bernoulli equation is applied to it. For steady and incompressible flow, the sum of the mechanical energy, potential energy, and kinetic energy along a streamline is constant. Any increase in one form results in a decrease of another. If there is no change in height along a streamline, Bernoulli's equation becomes a balance between static pressure and velocity.
Next, we will look at the use of streaklines in visualizing the character of flow. When the lines are parallel to one another with no lateral mixing, it can be said that the flow is laminar. When the angle of attack on the airfoil is increased, we see eddies forming at the tail. We can also see the layers mixing with one another. This is characterized as a turbulent flow.
For real-world application, smaller scale models of airfoils or other geometries can be used to visualize fluid flow around the objects. In terms of airfoil, this can help create designs that optimize lift while keeping turbulence at a minimum.